Half-life is the time required for the concentration of a reactant to decrease to half of its initial concentration. So how much time does it take for half of your compound to react? All right, so you can actually take, for first-order reactions, our first-order equation and rearrange it to find the time needed for half of your compound to react. So you don't need to be able to derive this if you can just memorize this equation. The half-life, the time for half of your compound to react, is equal to 0.693 over K for first-order reactions. Now, for first-order reactions, which you recall are generally decomposition reactions, that is, a compound just spontaneously changes into B without a collision, then the likelihood of A turning into B is unaffected by the presence of other A's, because collisions are not necessary. Considering that, the half-life is not dependent upon the concentration either. If the likelihood of A turning into B is unaffected by the concentration of A, then the half-life is also unaffected by the concentration of A. You can see that in our equation here. The half-life is equal to 0.693 over K. There is no concentration of A in this equation. And so, what is half-life? Well, it allows you to fairly easily predict how much compound will remain at a given time. So let's say that your compound or your mixture, your sample, has gone through 0 half-lives. Then you start with, say, 1 molar of it, or 100% of what you started with. But after 1 half-life, you've lost half of what you started with, and so half remains. Or if we had started with 1 molar, we would be left with 0.5 molar at our first half-life. And by the time we get to our second half-life, we've lost another half of what we had at the most previous half-life. And so half of that 0.5 is 0.25. And then by the next half-life, we've lost half of what we had at the second half-life. And so half of that 0.25 is 0.125. So we lose decreasing amounts over time. A lot, half as much, half as much. Each half-life we go through, we have less compound, and hence the rate of the reaction decreases as well, and we'll lose half as much as previously. And so you want to consider this chart. After 1 half-life, 50% remains. 2 half-lives, half of that, or 25. 3 half-lives, 12.5. 4 half-lives, 6.75. 5, half of 6.75, etc. Okay, so we can use these concepts to solve some problems like what is the half-life of a decomposition of N2O5 if its rate constant is 5.7 times 10 to the negative 4 reciprocal seconds? Well, half-life is equal to 0.693 over K, so plug in for K. And we get 1200 watt unit. Our half-life is seconds or minutes? Well, our rate constant is in reciprocal seconds, so we'll be left with seconds here. And so that would be 20 minutes. So the half-life is 20 minutes for this decomposition. Now, continuing with this problem, if its half-life is 20 minutes, what concentration will remain after 40 minutes if you start with 0.40 molar of it? All right, so if you start with 0.40 molar, how much remains after 40 minutes? Well, how many half-lives have you gone through? If a half-life is 20 minutes and it's reacted for 40 minutes, it's reacted for 40 over 20, 2 half-lives. So divide the total amount of time by the half-life, and that tells you the number of half-lives that the reaction has proceeded. And so if it's proceeded for 2 half-lives, you know that 25% of your compound remains. And so if 25% of that 0.40 molar remains then 0.25 times 40, 0.40 molar, is going to be 0.10 molar remains. So this is a very simple problem, but what if you're given a number which is not going to give you a whole number of half-lives? What if you don't get a clear-cut number of half-lives? Well, this is the case if I asked you what molarity would remain if the reaction proceeded for 45 minutes. Well then, you know that 20 minutes is one half-life, and 40 minutes is two half-lives, and 60 minutes is three half-lives. You don't have given a whole number of half-lives, so you have to take your half-life and solve for rate constant. Half-life is equal to 0.693 over k, and k is equal to 0.693 over half-life. 0.693 over 20 minutes, the rate constant is 0.0347 reciprocal minutes, 1 over minutes. Now, with your rate constant, knowing the amount of time that the reaction proceeds and the concentration that you began with, you can solve for the concentration that will remain. And so, just like in our first order reactions video, we see that the concentration that remains can be found by getting rid of the natural log, taking the e to the whatever value you had here, so e to the negative 2.48 gets rid of the natural log, and so the concentration that remains is 0.0841 molar. Now does this make sense? Because you're always checking your answers. After 40 minutes, you just saw that you had gone through two half-lives, and you went from 0.40 molar to 0.10 molar. Now, what if you've gone through 45 minutes, slightly more than two half-lives, then you would have lost slightly more than you had previously. You'd be a little bit lower than 0.10 molar. About 0.084 makes sense. Of course, if you'd gone through three half-lives, you would have gone to 0.05, half of that 0.10. And obviously, you shouldn't have gone through another half-life because that would have been at 60 minutes, not 45. All right, thanks for watching, guys.